We're spending time talking about and solving these linear systems, but where are we going to come across them when we're dealing with engineering type of problems? Well, these are going to crop up a lot whenever we're doing numerical evaluation of various types of systems, depending on your discipline, mechanical engineering, electrical engineering, chemical, something like that. These different types of systems are going to often crop up with a lot of linear equations that we're going to need to solve simultaneously. If you're going down a mechanical or a civil track, you're going to be looking at mechanical structures and analyzing the forces and the moments that are going to be involved in them. So if you take a course like Engineering Statics, EMEC 211, or a course like Strength and Materials, EMEC 213, you're going to be dealing with creating these systems of equations and then needing to solve them. In a thermal type of course, like a heat transfer course, we might be breaking a large plate or other object down into a grid to try to analyze what the temperature is at different locations on it, and we might be doing that numerically. Again, we're going to be creating a whole set of linear equations that we need to solve simultaneously. Similar things in electrical systems. If we have a circuit built and we want to know what the voltages are, the voltage drops are across different elements in our circuit, a linear system of equations will probably be produced. And if we're conducting finite element analysis on any of these types of things, the whole premise of a finite element analysis is creating a very large linear system and then solving all those equations simultaneously. So what's going to happen is either we'll have a smaller set of equations that we don't want to solve by hand or we need to automate, or depending on what we're looking at, it could be a very large system of linearly independent equations that we need to solve simultaneously in these various fields. And this leads us to another aspect of how linear systems are used in physics engines in computer simulations. So what we try to do is simulate the interaction of large-scale dynamic systems by creating a system of linear equations that we want to solve. Now sometimes these are solved in post-processing, so we don't need to do it in real time. So if we're trying to simulate the flow of some fluid through a pipe or some air over an airfoil, then we might be putting it into a physics engine and then solving repeatedly sets of linear equations so we can solve for the different velocities and different pressures as time goes forward over the aircraft, say. But in real time, we're often concerned about these physics engines and solving for the interaction of different physical objects in things like video games or other real-time simulations. So several of these different engines that these games use, the Havoc engine, more popular, the Unreal engine or the Unity engine, are trying to create linear systems and then solve them as quickly as possible. And really, most graphics cards that you have, all they do is very, very quickly solve these linear systems of equations so that it appears to be happening in real time. Now, if we were doing a slow process, like trying to invert the matrix, or we were trying to use reduced row echelon form, which we saw previously can take a lot longer than these different methods for solving the linear systems, then if we're trying to run something in real time, some kind of simulation like a video game to know where the character is, or if they're jumping, or if they're going to hit a wall if they're walking forward, if we're trying to do that in real time and we have a very slow process to solve these linear systems of equations, then it's going to be very choppy and it's not going to flow in real time. So the faster we can solve the equations, then the more realistic and the higher frame rate that we're going to be able to get.